Hello friends, welcome to aptdemy's calculus course for AP/AB test. Today's module is on differential equation. It's a very important topic. These are the subchapters to be covered in today's module. So for this program, this module, you need to have prior knowledge of differential and integral calculus that we have already covered. And these are the reference book for differential equation. Okay. Now, earlier I told that three main pillars of calculus. One is differential calculus, another is integral calculus, and another is differential equation. Differential equations, what they are actually? Differential equations relate functions of an independent variable and their derivatives. Say y is a function of x. So differential equation is something which connects y, its derivatives. This is first derivative, this is second derivative, this is third derivative, and so on, maybe nth derivative. So it is a equation which connects all these quantities, okay, so by some functional relationship. Now generally when we model physical systems or processes in science, physics, mathematics, physics, chemistry, engineering, technology, generally physical process modeling of physical system or processes require involvement of different physical quantities and their rate of changes, okay, and these rate of changes are connected by equations which involve the unknown functions and their derivatives, maybe first derivative, second derivative, nth order derivative also, and these equations are called differential equations. Here fx is an unknown function of independent variable x, and fnx is the nth derivative of fx. Okay. Okay. Now, by solving differential equation, so differential equation connects unknown function and their derivatives, and by solving the differential equations, we generally determine y as a function of x. Okay. So from differential equation, by solving differential equation, we get this type of solution y equal to fx, which connects y and x through some mathematical analytical relationship. Differential equations involving unknown functions of single variable come under the category of ordinary differential equation, and partial differential equations involve unknown functions which is a function of two or more variables. In this course, we will only consider ordinary differential equations, that means where unknown function is function of a single variable x. When, as I told, the differential equation connects the unknown function and its derivatives like y, y dash, etc. If this unknown function y, its first derivative, second derivative, and so on, maybe nth derivative also, if they are connected by a linear relationship, okay, then it is a linear differential equation. If they are connected by nonlinear relationship, then it is a nonlinear differential equation. So a linear differential equation is a differential equation that is defined by a linear combination of unknown function y and its derivatives. And nonlinear differential equation is one which is defined by a nonlinear combination of the unknown function y and its derivatives. Okay. If in a differential equation, be it linear or nonlinear, the highest order derivative involved in that equation is, if it is fnx, that means nth derivative, or say you can say yn, That means nth derivative of y, if it is involved in that differential equation, then we say the differential equation is nth order differential equation. Okay, that means in a differential equation, a term like dny dxn is appearing, n is an integer, then we say it is the nth order differential equation. And this is, say for example, this is a differential equation, y dashed plus px y equal to qx. Y dashed is nothing but dy dx, and y is actually a function of x. This is the unknown function to be determined by solving the differential equation. So this is an example of differential equation, or in other words we can write dy dx plus px multiplied by y equal to qx, where px and qx are functions of x. Okay, so this is a linear differential equation where you see y dashed and y, there is a linear combination of these terms, only y dashed and y are involved, and px and qx are functions of x. Okay, and the highest differential operator appearing in the differential equation is dy dx. So it is a first order differential equation. Had there been a term like dny dxn plus px y equal to qx, then we call this differential equation is the nth order differential equation. This equation is a first order differential equation. And in this module for APAB exam, we need to consider only first order linear differential equation. Okay, that means only linear terms of y and y dash and are involved. There is no term above y dash. That means second order, third order differential operators are not available in the expression. And y is function of a single variable which is x. Okay, so this is a first order linear differential equation. Y dash equal to px y plus qx. So once a differential equation is given, our objective is to solve for y. That means find a solution of the differential equation. Finding a solution of a differential equation like this is to find an expression for y which satisfies the given differential equation. To find an expression for y as a function of x which satisfies the given differential equation. Okay. Now, as I was telling that in physical systems, actually, we generally need to handle an unknown quantity and its derivatives or rate of changes. Say, for example, in last 400 years, more than 400 years, the most influential law in science is undoubtedly Newton's second law, which talks about acceleration of a particle under influence of an external force. Okay, so we know that if P is the applied force on an object, then it is connected by this equation mf. Okay, and when say a particle is moving along straight line, rectilinear motion, and if this direction is x, then m acceleration we can write as d2x dt square is the applied force, which may be a function of x, which may be a function of other variables also. So this is a differential equation, and generally while solving the mechanics problem, we begin with this type of equation, which is a differential equation of second order. Second order differential equation, and it's a linear because only d2x dt square is, in this case, t is independent variable and x is a function of t. Okay, and x dash, only x double dash term is appearing, that's why it is second order. There is no higher order term, and this is a linear term because there is no appearance of x dash square or sine x double dash type things. No nonlinear term is appearing in the expression, so it is a linear second order differential equation, and in mechanics problems we need to solve such type of equations. Okay, so mostly in physics and engineering you will connect, you will get some equations which involve the unknown quantity and its derivatives, and you always begin with such differential equations, and under certain boundary conditions or initial conditions you need to solve the differential equation, and you obtain the solution of the unknown in terms of the independent variable, and thereby you model the physical system. Okay, now it has, as I told, differential equation has influence in every branch of sciences and technology. Let us consider a few geometrical problems. Okay, like this. Say, consider n number of concentric circles. This is 0, 0 origin. Centering around origin, there are concentric circles, and the circles are like this: x square plus y square equal to 1, x square plus y square equal to 2, like this. Consider n number of such circles. X square plus y square equal to n. These are different circles. Okay, they are represented by different colors, and sometimes it is solid line, sometimes it is broken line, broken curve. Okay, now all this equation, wherever it is this side, right hand side, some quantity is there which is related to the radius of the circle. It is radius square. That means the first circle is a circle whose radius is 1, second circle is a circle whose radius is square root of 2, nth circle is a circle whose radius is square root of n. Okay, but irrespective of the radius, if we differentiate any arbitrary general circle, I can write as k square. This is k. Sorry, let us write k only. K is an integer. Say for example, okay, we have chosen circles such that the RHS of these circles, equation of the circles is the integer. So k circle you can say, that means its radius is square root of k, this particular circle. Now if you differentiate the equation of the circle, it becomes 2x plus 2y dy dx, 2y dy dx is equal to 0, or you can write x plus y dy dx equal to 0. Now what is interesting is that you take any of the n circles, if you begin with any of these n equations, you arrive at this equation. So for all circles, though their algebraic equations are different, but they have a common differential equation. That means this common differential equation represents this bunch of circles, the set of circles, set of all concentric circles. So this set of n algebraic equations representing n circles can be represented as a single first order ordinary linear differential equation. Single first order, because there is no term higher involving y double dash or higher order terms. So it is a first order differential equation. It is a linear differential equation, and only linear terms of y and y dash are involved, and this is a ordinary differential equation because y can be expressed as a function of x. If you take any of this equation, y can be expressed as a function of single variable x. Okay, so this equation represents a set of concentric circles, okay, like this. So this set of n number of concentric circles can be represented by a single differential equation like this. Now, if we begin with the equations of circles, we can find this as a equation, differential equation representing the set of concentric circles. Similarly, if you are given with this equation, if you begin with the differential equation, then you can solve the differential equation and you arrive at circles. And the solution of this differential equation, how to solve this differential equation, we do not know at present, but the solution would be like this. Okay. By solving the above differential equation, we get general solution of the concentric circles like this: x square plus y square equal to k. And here k is an arbitrary constant with imposition of some conditions. We can pick up or pinpoint a particular circle, say this circle, blue circle, if we want to pinpoint. That means we are pinpointing a circle whose radius is this much. So by some mathematical clue, if we specify the radius of a particular circle, then we can arrive at a particular solution of this differential equation, maybe the blue circle. Okay. Okay. So we at this moment we do not know how to solve this differential equation, but we can verify that this is a solution of this differential equation, because by differentiating this equation we can arrive at this, as we have already shown, that 2x plus 2y dy dx is equal to 0. Therefore, x plus y dy dx is 0, which is this equation. Okay, but how to get this equation from that, it is not yet known to us. Okay. Okay, now let us consider another example. Here actually we have a set of, say, 5 straight lines. This straight line is passing through origin. This straight line 1 is also passing through origin. This is a straight line which is having positive intercept on both x and y axis. Green straight line is a straight line which is have a negative intercept on x axis and positive intercept on y axis. And this straight line number 5, which is having negative intercept on y axis and positive intercept on x axis. Now, all the set of 5 algebraic equations representing 5 straight lines are like this. You see different: y equal to x, y equal to negative x, y equal to 1 minus x, y equal to 1 plus x, and y equal to x minus y. These are the different straight lines shown in this diagram. Now, whatever be the straight line, it can be represented by this type of equation. Say d2y, say begin with this one, first one, y equal to x. So if you y dash is 1, y double dash is 0. So y double dash is d2y dx square is 0. Second one, if you take y equal to negative x, so y dash is negative 1, y double dash is 0. Third one you consider y equal to 1 minus x. So y dash is negative 1 and y double dash is 0. Fourth one you consider y is equal to 1 plus x. So y dash is 1, y double dash is 0. Fifth one you consider y equal to x minus 1, then y dash is 1 and y double dash is 0. So you see, in all the cases, starting with the algebraic equation, we get equation like this, y double dash equal to 0, or in otherwise d2y dx square is equal to 0. So this is all these 5 straight lines can be represented by a single second order differential equation d2y dx square equal to 0. So from the algebraic equation you can get this type of differential equation. So possibly by solving the differential equation d2y dx square, you will get a set of straight lines. By solving the above differential equation, we get the general solution of the straight lines, and the general solution of, we do not know how to solve this equation, but take it from me, the general solution of this equation will be something like ax y equal to ax plus b. And you see, by suitable combination of a and b, you can get any of these equations. Say for example, the first equation a is 1, b is 0. The second equation, where a is negative 1, b is 0. The third equation, a is negative 1 and b is positive 1. Fourth equation, a is positive 1, b is positive 1. And fifth equation, a is 1, b is negative 1. So with imposition of some conditions, say for example, the first one, if we say that my straight line, desired straight line is passing through origin, then we may get either of this or that. And with imposition of another condition, I can pinpoint which straight line, this or that, we are interested in. Okay. So generally, since it is a second order differential equation, solution involves two unknown constants, a and b. And we need two conditions to evaluate these constants a and b. Okay. If it is a first order differential equation, generally the solution involves one arbitrary constant, and with imposition of one condition we can evaluate that unknown constant. It is a second order differential equation, linear second order ordinary differential equation. Here two solution will involve two arbitrary constants, and with imposition of certain boundary conditions or initial conditions, you can evaluate a and b, and two such conditions are required to evaluate the conditions. Okay. So when you are provided with a set of algebraic equation, you can find out what is the differential equation representing those algebraic equations. And when you are provided with a differential equation, you can solve for the differential equation to find the general solution for y. And if you are interested in a particular solution, that means if you want to pinpoint a particular straight line out of this set, we need to specify certain boundary conditions, initial conditions. So you will see how it is done. And generally, if it is a first order differential equation, to evaluate the constant, we need at least one boundary condition, because in first order general solution of first order differential equation will involve a single arbitrary constant, whereas if it is a second order differential equation, it will involve two arbitrary constants, and you need two conditions to evaluate those constants. Okay. Now consider the motion of a particle along a straight line. Straight line is x-axis with constant acceleration f. There may be several situations like this. Particle starts its motion at x equal to 0 with some initial velocity. So if it starts its motion at x equal to 0 with some initial velocity, we know from kinematics that in that case x, that is the displacement of the particle, can be written as x equal to ut plus half ft square. This is the first case. Particle starts its motion at x equal to a with some initial velocity u. That means in that case, this equation says that at t equal to 0, x is 0. Okay. Second situation, particle starts its motion at x equal to 0, x equal to a with some initial velocity. That means at t equal to 0, the particle's displacement is a. So its equation, expression of x will be like this. Okay. Third case is particle starts its motion at x equal to 0 with 0 initial velocity. So in that case, its expression for x will be half ft square. This is third situation. And fourth situation, particle starts its motion at x equal to 0, x equal to a with 0 initial velocity. So in that case, expression for x will be like this. Particle starts its motion at x equal to a with 0 initial velocity, but it has a acceleration, uniform acceleration, so it will be a plus half ft square. This is fourth situation. You see, x is function of t, or you can write x is equal to x of t. It is a function of t. T is the independent variable. And now whatever be the situation, you take whatever be the situation, start from 1, differentiate with respect to x with respect to t. What you will get? Dx dt is u plus ft, and d2x dt square will be f. Second, same thing, a is constant, so you will get the same thing, d2x dt square equal to f. Third case, you see this one, third case, x dx dt is, in that case, third case, in third situation, dx dt will be, this is third case, dx dt will be ft, and sorry, dx dt will be ft. Third case given equation is this thing, so dx dt will be ft, and d2x dt square will be definitely f. Fourth case, this is x equal to a plus half ft square, dx dt will be ft, and d2x dt square will be f. So whatever be the case, whatever be the situation, you see all cases, we start from the algebraic equation, we arrive at this expression in all the cases. Okay, that means this is the differential equation describing the motion. Okay, and whatever all these things, the general solution, this expression will be like this, the differential equation will be like this. Okay, and this is a second order ordinary linear differential equation. Okay. So whatever be the algebraic equation, these or these or these or this, you verify it is d2x dt square is f for all the cases. where f is what? F is the acceleration, uniform acceleration of the particle. And since it is a second order differential equation, solution of this equation will involve two unknown constants, and it can be shown, though we have not learnt how to solve this equation, but its solution will look like some constant half ft square plus pt plus q, where p, q are constants. Because this is the solution of this equation, because this solution, this is arbitrary constant, say p and q. If you differentiate x dx dt, it will be ft, first term will contribute ft plus p, because p is a constant, so ddt of pt is p only, and d2x dt square is f. So this expression for x is a solution, general solution of this equation, and with imposition of some boundary conditions, you can find out the values of p and q. So it can be verified that the general solution of the above differential equation is, above differential equation means this, it's a second order linear ordinary differential equation is like this. Whatever you have written, x equal to half ft square plus pt plus q, where p, q are arbitrary constants. P, q can be evaluated with imposition of initial conditions, and we need to evaluate p and q, we need two initial conditions, and when we can find out the values of p and q, any of the four situations we can find out actually. Okay. So what we are trying to give is to emphasize is that some physical systems, geometrical problems, it may be represented by several algebraic equations, but by a single differential equation, all these things, all these situations can be described by imposition of proper initial conditions, physical conditions you can say. Okay. Okay. Now, verifying solutions for differential equation. So we started with the first order linear differential, started with some algebraic equations, and we could verify that we could derive a differential equation representing the algebraic equations. Similarly, if you are given a differential equation, there must be some techniques by which the differential equation can be solved, and you can find y as a function of x. Now, sometimes it is necessary that to verify that some solution is a solution for differential equation. Verify that in this exercise, verify that x square plus y square equal to 2 is a particular solution for differential equation this. So begin with this, differentiate, and you get x square plus y square equal to 2. So 2x, already you have discussed 2x plus 2y dy dx is equal to 0. So x plus y dy dx is equal to 0. Okay, so this is the differential equation. So it is a solution of this differential equation. This is a particular solution because instead of 2, if you write anything like k, then also you get this solution. So x square plus y square equal to k. K is not, it's an arbitrary constant. This is also a solution of this differential equation, x plus y dy dx. So this is a general solution of this differential equation, And when k value is 2, we call it a particular solution of the differential equation. Okay. In general, x square plus y square equal to k is a general solution of the differential equation, and x square plus y square equal to 2 is a particular solution of the same differential equation. Okay. So x square, it is not x square plus y square equal to 2 is one among many solutions of this equation. General solution will look like this, where k can take any value. Any k can be any number, and when k assumes a value 2, we pinpoint to a particular solution of the differential equation. Okay. Say for example, this is another example, another problem. Verify that y equal to ax plus b is a general solution of this differential equation. So begin with y equal to ax plus b, dy dx. A and b are constants, arbitrary constants. This is a, and d2y dx square is 0. So y equal to ax plus b is a general solution of this d2y dx, this differential equation, d2y dx square plus 0 equal to 0. Say a equal to 3, let us consider a equal to 3 and b equal to 5. Say a equal to negative 3, then y is negative 3x plus 5. So in that case also d2y dx square will be 0, because dy dx is negative of 3 and d2y dx square will be 0. So this equation has got a solution like this also, y equal to negative of 3x plus 5. But this is a particular solution, because a, b can take any arbitrary value, and in all cases, whatever value you think a and b, it satisfies this differential equation. So this is a particular solution of the differential equation, whereas this is a general solution of differential equations. So this equation represent set of all straight lines y equal to ax plus b. Y equal to ax plus b is a set of, it represents the equation of a straight line, arbitrary straight line in the xy plane. Okay, so arbitrary straight line, any straight line, arbitrary straight line, their equation will look like this. Differential equation will look like this. An algebraic equation for the straight lines may look like this, but the differential equation looks like this. Okay. So any first order linear differential equation can be expressed as dy dx equal to a function of x and y, but only thing is that since it is a linear equation, the terms y and y dashed, they will appear in as a linear term. That means no y square or sine y or ln y dashed. This type of terms are not there in the linear differential equation. We can now, another thing before that, okay. 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 Now let us consider this one. The very important concept which is called slope field of a differential equation. Sketching slope fields, what do you understand by slope fields of a differential equation? Any first order linear differential equation, ordinary linear differential equation may look like this, where y and y dashed are only involved and they appear in the equation in linear terms only. Okay. Now, when you are provided with a differential equation, we can compute the value of dy dx at different xy points, because this is a analytical expression for dy dx. So, at different xy points, you calculate the value of dy dx. Okay. And dy dx is what? Dy dx is, if y equal to fx is the solution of this differential equation, then at the point xy, if you draw a tangent, then the slope of the tangent will be dy dx. Okay. Now, if we can compute the value of dy dx at different xy points and graphically represents the slopes by drawing small line segments of tangent at those points, then we get the sketch of slope fields of y equal to fx plus k, which is the general solution of the differential equation. Okay. So, given differential equation dy dx is gxy, which is function of xy, if its solution is something like this, then dy dx values at different xy points, if you can compute and if you can plot the slopes properly, then that is called the slope field of the differential equation. A slope field is a general graphical representation of a differential equation on a finite set of points in the xy plane. Slope fields provide information about the behavior of solutions to ordinary first order differential equations without even solving the differential equation. Okay, so things will be clear with example. Let us now, this differential equation, as we have discussed several differential equations in different situations, generally it is dy dx equal to gxy. There may be a constant, separate constant terms also. So, this is a differential equation. Now, algebraic equation, solution of this is, say, example, y equal to fx plus k. Okay. Now, this algebraic equation is a solution of this differential equation. Both are identical things. This algebraic equation is hidden inside the differential equation, we say. And the same can be extracted only after solving the differential equation. So, it requires solving the differential equation. There are very many techniques for solving a differential equation. It's a subject itself. Solving differential equation itself is a very big subject, very vast subject. But if it is a first order differential equation, if we can compute the values of dy dx at different xy points, and if you can plot them, if you can sketch the slope field of the differential equation, we can at least guess about the geometrical structure of the general solution of the differential equation. That is the advantage, and it gives you an insight about the solution of differential equation. Okay. Say, for example, let us begin with a differential equation. The differential equation is very simple. Say, for example, dy dx, which said is generally, we discussed that dy dx is function of xy. Some constant also may come into picture, but in our case, let us begin with a very simple example where dy dx is constant and the value of the constant is unity. So, dy dx a given differential equation is this one. This is definitely first order linear ordinary differential equation. There is no other variable involved. Okay. Now, irrespective of the value of x and y, solution of this differential equation we do not know. Y equal to some function of x. It may be the solution of this differential equation. We do not know. But whatever be the solution, irrespective of value of x and y, x being the independent variable, y is the dependent variable, value of dy dx at all points on the solution will be unity. So if you make a table like this, x, y, whether it is 0, 0, 2, 1, 0, 2, negative 2, 0, whatever, x1, y1, any arbitrary point on xy plane, dy dx is 1. Dy dx is what? It is the slope of the tangent at that point. So dy dx is nothing but tan of theta, where theta is the angle. So if y equal to fx is the solution, then at xy point, if we draw the tangent xy point, then tan of theta is actually dy dx computed at the point xy. So it indicates at all points the tangent is making an angle 45 degree. Dy dx is equal to tan theta, so theta is tan inverse dy dx. Since dy dx is 1 everywhere, so theta is 45 degree everywhere. So you take any point on xy plane, if you draw the tangent at that point to the solution curve, then it will make an angle 45 degree. So these are different points on xy planes. I have drawn only a few points over here, but whatever be the point, if it is this point, here also it is like that, if it is this point, here also it is like that, making an angle 45 degree. So solution will be something for which if you compute dy dx it is 1. Okay, that means actually your solution is what? Its solution will be set of all straight lines having gradient 1. So set of all straight lines having gradient 1, that means all straight lines like this, all straight lines on the xy plane, take any straight line whose gradient is 1 like this, then this entire set of straight lines will be represented by this differential equation. Okay. Once again, this is the xy plane, this is the xy plane, and you draw all straight lines making an angle 45 degree. How many such straight lines are possible? Infinite number of straight lines are possible. And you take any point on the straight line and draw a tangent, tangent of a straight line, tangent drawn at any point on the straight line is the straight line itself, and since the straight line itself is making an angle 45 degree, wherever you go, it is always 45 degree. So this will be the straight line, tangent drawn on a straight line at a particular point is the straight line itself. So this will be set of all parallel straight lines, and they are parallel to each other and they are all making angle 45 degree with x-axis. Okay, so slope field reveals that the solution will be like this, and set of all straight lines having gradient 1, we can say that solution y that can be represented by y equal to x plus k, because y equal to x plus k represents a straight line which makes an angle 45 degree with x-axis. So y equal to x plus k, we can represent all such straight lines having making angle 45 degree with x-axis. Okay, so this is the significance of slope field. Say you are given a differential equation. So differential equation is dy dx is equal to negative of x by y. then what is the slope field of this differential equation? So if you take different points, say for example 0, 0 point. Here 0, 0 point, if you want to calculate dy dx, it becomes 0 by 0, it is indeterminate. So 0, 0 point dy dx cannot be determined. Okay, so let us exclude 0, 0 point. 0, 1 point, x equal to 0, y equal to 1. So it is dy dx is 0. That means the slope will make an angle, the tangent will make an angle 0 degree. That means 0, 1 point means this point. So slope field will look like this, making an angle 0 degree. This is the slope field. Tangent line, this is the line. 1, 0 point, 1, 0 point, x equal to 1, y equal to 0. So it is dy dx becomes infinity sort of thing, and that means it is making an angle 90 degree with the x axis. 1, 0 point is x equal to 1, y equal to 0. So the tangent line will be like this. This is 1, 0 point. Negative 1, 0. Negative 1, 0 also it is something divided by 0. So it makes an angle like 90 degree with the x axis. Whether it is positive 90 degree, this or this, it is immaterial. In both cases, the magnitude of dy dx is infinity. So this is then 0, negative 1. X equal to 0, y equal to negative 1. X equal to 0, y equal to negative 1. X equal to 0, y equal to negative 1. So again dy dx becomes 0. So at this point it will be like this, making an angle 0 degree with the x axis. 1, 1. 1, 1 point means dy dx is 1, negative of 1. That means tan theta is, as I told, tan theta is dy dx. So theta is tan inverse dy dx. So tan inverse negative 1. So theta will become 135 degree, because tan 135 degree, tan value of tan 135 degree is negative 1. So at 1, 1 point, say like this, it will make an angle 135 degree with the x axis. That's why it is like this. So if you calculate theta from this table, from this expression, you will get plots like this. Okay. So when the differential equation is given, it is a first order differential equation. That means there is no terms other than dy dx. Higher order derivatives are not involved. Only dy dx is involved in the differential equation. So if you can plug in different values of xy in the given differential equation, you can compute the value of dy dx at those points and then calculate theta. That means how much angle the tangent at that point makes with positive x axis, and draw small line segments maintaining the angle actually. Okay, and then you can get the slope fields. And what this slope field indicates, that means solution of the differential equation will be such that if we draw tangent to the solution curve at these points, the tangents will be like this. That means at this point, if we draw the tangent to the solution curve, the tangent will be like this, in this direction. At this point, the tangent will be like this. At this point, the tangent will be like this. At this point, the tangent will be like this. So once you draw the slope fields, actually you get the orientation of the tangents drawn to the solution curve at the given xy points. Okay, so you can make a guess about the solution of the differential equation. And you see here, it is basically the solution of the differential equation will be like concentric circles. Okay, concentric circles, because if it is a circle, its slopes at different points will be like this. So these 4 points, here the slope is making, tangent is making 0 degree with x-axis, here the tangent is making 90 degree with the x-axis, here the tangent is making 0 degree with x-axis, here the tangent is making 90 degree with x-axis. Consider this particular circle. Like this. Consider this circle. So here this is the tangent, 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 and here it is making 135 degree with positive x-axis, here the tangent is making 45 degree with x-axis, here tangent is making 135 degree with x-axis, here tangent is making 45 degree with x-axis. So here this is another circle maybe, and this is the tangent here, this is the tangent here, this is the tangent here, this is the tangent here. So slope fields indicate a deep inspection into the slope field plot indicates the solution will be like concentric circles. That means if you on the slope fields, if you superimpose the dotted circles, then definitely the dotted circles, the tangents, these are the tangents to the solution, and only these dotted circles, they match with the tangents if it is concentric circle, if this set is a set of concentric circles. Okay, so from the slope field, what you can guess about the solution? All concentric circles centering origin. Okay, so dy dx equal to negative of xy, negative of x by y. We do not know how to solve the equation, differential equation so far, but we can guess that the solution of this differential equation will represent set of concentric circles. Okay, and set of concentric circles will be what? That their equation will be like this: x square plus y square equal to k. Because this is the set of concentric circle, for different k values we get different circles, and all such circles they are concentric because for all such circles the center is at 0, 0. And if you differentiate 2x plus 2y dy dx, equal to 0. Therefore, y dy dx is negative of x. So, dy dx is negative of x by y. So, what we guessed that by plotting the slope field of this differential equation, this was the slope field, and we could guess that the solution will represent the set of concentric circles, and we could easily write the equation for set of concentric circles centering origin, this point. So these are the points. This is so these concentric circles, they, if we take derivative with respect to x, we arrive at this equation, which is the given differential equation. Therefore, set of concentric circles truly represent this differential equation. That means the solution of this differential equation will be set of concentric circles, and that we could guess from the slope field itself. Till now we do not know how to solve this differential equation, but from the slope field we can make a very good guess about the probable solution of the differential equation. And see here, at 0, 0 point, there is no circle like this. 0, 0 is a point, and there is no concept of drawing tangent. It is excluded actually. That its radius is not defined. It is a 0, 0 point. So at this point, this differential equation has no significance as such. because dy dx is undefined. Okay, but other than 0, 0, this differential equation has a meaning, and that represents, differential equation represents set of concentric circles. Okay.